Okay, everyone, good morning. I see some more people joining in, and I think some people are having some trouble with the registration links, so we are trying to help them sort it out. But let's get started here, and maybe other people will join in as we help them out, okay? Okay, so today I'm very happy to invite Professor Maya Ramanath as our second speaker for the Data Conversation Initiative. Just to remind, this is an initiative that we started a month back with the goal of getting data researchers, students, practitioners onto the same platform. And our first activity is we are doing monthly seminar series where eminent speakers who have been doing a lot of work in this space would go, come and talk about their work, and hopefully that would hopefully that will help with more ideas, more questions, and potentially more collaborations. So one of the places of how you could collaborate is via the Slack channel. So I will be sharing that in the link later on the Zoom. So please, if you've not joined it, please plan to join. And for all the questions for the talk, please put it on the Slack channel. We will read it out at the end of the talk and read it out at the end of the talk, and for during the Q&A session. Okay, with that, let me once again invite Professor Maya Ramanath. She doesn't need any introduction. She has been working in the spaces of databases for several years. She is an associate professor in the Department of Computer Science and Engineering at IIT Delhi. And before that, she was a postdoctoral researcher in the Database and Information Systems group at Max Planck Institute. And before that, she was with IISc and so on. Today, she's going to talk on a very interesting topic on domain-specific knowledge graph construction and applications. And she's going to be talking about her work on knowledge graph construction techniques for various different domains. And then she'll also talk about applications that make sense only for a certain domain and can be implemented on top of these knowledge graphs. And underlying, I think, interesting and important trick here is that all of this work, right, is going to be where they're trying to avoid supervised ML techniques, and that makes a lot of sense because at least in enterprise settings, it's really hard to get so much label data to build knowledge graph constructions. So the whole world has been moving towards how to utilize unsupervised data towards this large-scale enterprise use cases. So with that, once again, I invite you, Professor Maya, and I would hand it over to you.
Yeah, thanks, Hima. Thanks, everybody, for coming to this talk. So what Hima said at the end, having no supervision for constructing these knowledge graphs, she was absolutely right. For the reason why we don't have the supervision, because of a lack of data, that is one reason. And the other reason is that I personally have never been very comfortable with machine learning algorithms, especially deep learning architectures and so on, because it always seems so mysterious how these things are, how these outputs are coming and what exactly was the mechanism and so on. So I guess it also has to do with a little bit of personal bias that I try my best to, apply techniques which I understand very thoroughly, what exactly happened to the input to provide a particular output. Right. Anyway, so today's talk is going to be at a very high level, not a lot of technical details. If you want to read about the technical details, you can always go to the papers and look at it. These knowledge graphs are something I have been working with since 2005. So that was when probably the first big knowledge graph, Yago, it was created while I was there in the Planck Institute. And in some way or the other, I have been associated with these knowledge graphs since that time. So querying knowledge graphs, it started with that, and then moved into things like domain-specific knowledge graphs, looking at very specific verticals and so on. So today I wanted to list a bunch of different applications that make sense to specific domains. So applications will be first part, and then we will look at the construction part. So just to make sure we all know what we are talking about, let me try to change the slide. Yeah, this is what I mean by a knowledge base. It's just a table with 3 columns. So there is the subject, predicate, and object. Subject and object you can regard as entities, and the predicate is a relationship between 2 entities. And here I have listed a bunch of triples. So at the top here in red, this is what you might call pop culture in a sense. And any knowledge base like DBpedia or Freebase or Yago, they contain a lot of triples from the popular culture. And this is not really of interest to us in this talk, right? Rather, what we are looking at is something that is more specific to certain domains, such as computer science, right? So here I have examples of triples that you could organize or extract from the computer science domain. You would have entities like topological sorting, classes like graph algorithm, and then you would have a relationship that topological sorting is a type of graph algorithm. And further, you might have graph algorithm is a type of algorithm, and so on. And here you can see other examples of relationships such as group testing is an application of coding theory. Gigabit Ethernet is a high-speed form of Ethernet, and so on. Okay, so entities and relationships which are specific to the domain of computer science. And then here in purple, I have some triples from the domain of politics, right? So this is an opinion base where the entities that you have here in subject and predicate, subject and object columns are topics. So here you have topics, and here you have stakeholders, such as they could be important political figures or organizations such as the UN or countries and so on. And the relationship here that we are interested in is just 2 relations, either support or oppose. Okay. So this is a very coarse-grained way of looking at opinions of certain stakeholders on certain topics. And lastly, here I have yet another set of triples from the domain of biochemical engineering, where again, the entities are all interesting in the domain of biochemical engineering. So Pseudomonas, for example, is a microbe, and hydrocarbon degradation is a process. And you have chemicals and you have environments as entities in the object column here. And of course, the predicates, Pseudomonas acts on acetone. That's a triple that makes sense in the domain of biochemical engineering. So what all this organization of data is leading up to, this is my favorite sort of thing that I put in every talk, is turn this entire web of information that we have, digital information that we have, into a knowledge base which is very well organized, machine readable, browsable, and self-maintaining encyclopedia. So it's like the entire human knowledge is organized in a very nice way for us now to use. Okay, so this knowledge base, which consists of just 3 columns here, of course, it is not actually achieving this goal, but it's a small step. And even with this, we can have some very interesting applications. So let me talk about some of these applications first, and then I will talk about construction and conclusion. So that is the outline of the talk today. So let's talk about applications. So the most obvious application I'm leaving out of it, which is question answering, right? So if you have an organized set of data and you want to retrieve data from it, and one way of doing that is to do question answering. So that is an obvious thing that I'm going to leave out of this talk entirely, and look at applications which are specific to the domains. So for opinion base, looking at something very vague called how do I explore the space of opinions? So when we built this opinion base, it was way back in 2012, right? So you might be wondering, why am I talking about work that is 10 years old? But it turns out that it fits very much into this theme of domain-specific knowledge graph construction. So I will show you that part later on. But for now, let's look at opinion base and some of the applications that are interesting on top of it. Right? So the first application I want to talk about is looking at flip-floppers. Right? So here is a set of stakeholders, and then here is a set of topics. And then we chose Barack Obama and drilling in the Arctic as the topic. And here are a bunch of opinions that Obama held about offshore drilling, basically. So drilling in the Arctic National Wildlife Preserve, it's all about offshore drilling. And we can see that there is a flip-flop that happened there. So he was at some point opposed to it, and then he was supporting, right? So, of course, this only gives an indication that perhaps Barack Obama had different opinions at different points in time. And if we actually want to know what was the context of these statements that he made or statements that he released, then we go to where exactly these triples came from, and then look into it. And it's a point of further investigation. So identifying flip-flops, if you have an opinion base, identifying such flip-flops on opinions is pretty much immediate. You do a query and you can get this. Secondly, there was this nice application looking at correlated opinions. So here I have two topics. So for example, carbon neutrality and offshore drilling, right? Carbon neutrality related to emissions trading. And typically, if a politician supports one of them, then they oppose the other. So that's what these dominant patterns here mean. So if it's a positive opinion about one of them, then it's a negative opinion in the other. If it's a negative opinion on the first, then it's a positive opinion on the other, right? So we have examples of politicians who, of course, hold these very dominant patterns. So this is nothing but the correlation coefficient that we are computing here. But at the same time, we can see that there are some dissenters. So you would expect a typical Republican to have one of these dominant patterns, but John McCain, who was a Republican, had positive opinions about both of them. So he is dissenting from the usual kind of opinions that Republicans typically have about this pair of topics, right? So finding the dissenting patterns, again, if you have the opinion base, you can simply look at the correlation coefficient of between pairs of topics, and then you can come up with a little bit of extra processing. You can come up with these patterns about who holds which opinion, and is it part of the norm or is it away from the norm. And then another application we had is a heat map of opinions. So on the y-axis here, you have many different topics, right? And on the x-axis here, you have news websites like Spiegel, France 24, BBC, and so on. So looking at news websites. So what we did here is to go to each of these websites and look at the articles that they have published and extract opinions from these articles. So we are trying to see if certain of these news organizations overly support or overly oppose some of the topics that we have. So, for example, if you look at Iran nuclear program and Fox News, they're sort of very much against it. So they keep publishing articles in which perhaps there are lots of quotes of politicians who say how much they oppose the Iran nuclear program, but not the case with, let's say, Al Jazeera, right? Similarly, if you look at Jerusalem Post, they're very much opposed to Iran nuclear program because they keep publishing articles of that nature. If you look at Palestine State, you would expect Jerusalem Post to be very much opposed to it, but not necessarily Al Jazeera, which writes lots of articles in support with it. So looking at this heat map, you can try to look at what is the slant of each of these different news organizations. Okay, so next let me move on to another set of triples here, which is looking at computer science topics. So we have a knowledge base called Technobase, and let me describe a couple of applications that we did on top of it. So the first one is academic search, which says which wants to solve this problem. How can I search for research articles discussing algorithms for autoencoders? And we all do it all the time. Probably every day we do multiple searches on Google to do this. Here I'm very much particular about the domain, which is computer science, and I want to look at research articles for discussing algorithms for autoencoders. So here is an example of such a search. This is Semantic Scholar. And one way to do this search is to simply enter autoencoder in the search box and you get a bunch of results, which are pretty good for autoencoders. But remember that our requirement was specifically on algorithms for autoencoders, which none of these are really quite relevant there. Okay, so we can try to expand the query, specifically saying autoencoder algorithm. So algorithms for autoencoders, but the set of results that we get again is not quite satisfying the user need, which is about algorithms for autoencoders. So it is mainly like a re-ranking of the results that were here. So with this problem in place, we decided to come up with our own ranking method, which would take into account the fact that there is a specific aspect of the topic that the user is interested in, right? So autoencoders, not in general, but a very specific aspect of autoencoders, which could be algorithms or implementation, application, and so on. So here is the kind of results that we got. So this is a snapshot of the actual results that we have from our system. And if you look at autoencoder and algorithm, you will see that the top result here is specifically about a training algorithm for autoencoders. So that satisfies the user's need, information need. So similarly, if you look at application, there is a very specific application that has been that is being explored in this particular paper. And I have other examples here, and there are more examples in the paper. Okay, so this is a nice academic search problem, but what does it have to do with knowledge graphs, right? So one of the ways in which we use the knowledge graph is as follows, right? So our so I'm going to just give you the idea of how we did it. There is lots of details that I'm leaving out here, but basically what we came up with is a mixture model, an LM-based method, right? So this is basically our method, a mixture model, where we compute the probability of a word. Now, what we are assuming here is that the probability of a word depends on the aspect. A is the aspect, and it depends on both the query as well as the aspect. So we want to calculate the probability of W given A and W given Q comma A. So remember, the input to this is that the user says, I want this particular topic like autoencoder as well as the aspect. So it could be algorithm or application and so on. So the user is giving us both the query as well as the aspect. And we want to compute these two probabilities and mix them to give our mixture model here. So what does this actually mean? So the first component, what we are trying to do is given the aspect like application, we want to boost the probability of certain terms like usage and used for and application. All of these terms indicate that this particular, these terms, if they are present in a particular article, then that means that article probably is discussing this very specific aspect of application. Similarly for the other aspects as well. And at the same time, if we consider this component where we are looking at both the query as well as the aspect, so we have autoencoder and application, there are a different set of terms which we want the probability of these terms to be boosted. So we wanted to make use of this mixture model, and in order to compute this particular probability, we could make use of our knowledge graph. How is that? We can see here that these triples that I've highlighted here, right? These three triples, they directly talk about the aspects of interest to us. So it directly says group testing is an application of coding theory. So you know that coding theory is a term which is of which, if given group testing and application as the aspect, then coding theory is a term of interest and its probability has to be boosted. Similarly, we have feature selection is an application of autoencoders. So feature selection is a term that is very relevant if the aspect is application and autoencoders is the topic, right? So its probability should be boosted. And so on for the other kinds of aspects as well. So I have one example of algorithm aspect. Heap sort would be a very relevant term if you're looking at the topic of sorting and the aspect is algorithm and so on. So I'm not going to go into details of exactly how we turn these, the presence of these triples into a probability. So there are some more details there. Actually, there are a lot of details there, but I urge you to go to the paper and, go through this method that we have. Right. So just a small set of results that we had to show that our method, the mixture model method, had pretty good results for the algorithm aspect. So this was over about 40 queries from the open research corpus, which has many papers from the computer science domain. So about 0.7 is the precision that we had. Not very successful for application and implementation aspects here, but at least better than some of the competing methods that we had. Right. So let me talk about another application using Technobase. And this is something that is sort of very close to my heart. This is about prerequisites to learn about a specific topic. And I think this is a problem that all of us have, especially these days when there are so many papers that are being published. It's hard to kind of keep track of what's happening. And then you suddenly come across a term that you don't know about. And you need to learn about it before you can go forward. And what we all do is go to Google and type in the name of, type in the term, and then we get this Wikipedia page. And in the Wikipedia page, you look at the first paragraph, and then there are a whole bunch of terms that, you may or may not know. So you have to click on that, which takes you to another Wikipedia page, and then another Wikipedia page, and so on, right? So this would be a very tiresome task until you sort of forget about what you actually started off with. So we wanted to build a system that will help in this task, right? So you just have to enter convolutional neural networks or any topic that you want to learn about, and it should give you a prerequisite graph of other topics that you should study before, which are prerequisites of convolutional neural networks. So there is some related work already when we started work on this to find prerequisites of entities. So we looked at some of them, and here is an example of the output that we get for convolutional neural networks. So that's here at the top. And many of the prerequisites that it is suggesting actually make sense, like backpropagation, perceptron, gradient descent, activation function, and so on. But we also see along with these prerequisites that there are things like MATLAB and Python, right? So sort of confusing why MATLAB and Python are mixed up with perceptron and backpropagation and so on. But actually a little bit of thinking actually gives the reason why these have come about as prerequisites. They all have to do with a specific aspect of learning about convolutional neural networks, right? So if you wanted to implement convolutional neural networks, then you need to know MATLAB or you need to know Python, the software, in order to, before you can actually implement CNNs. If you wanted to learn about the theory of neural networks, then you need to know about backpropagation and gradient descent and so on, which are again, you can look at them as algorithms that are directly relevant to understanding convolutional neural networks, right? So this is the idea that we had, that there might be a topic that a user is interested in, but in addition to that, there are also multiple aspects that can be separated out. So I've listed about 4 aspects here, all having to do with CNN. So if it is software, then you need to know MATLAB and Python. If you wanted to look at activation functions, then you had all these sigmoid, ReLU, and so on. If you wanted to know about applications of neural networks, which is yet another aspect, then you would need to know about things like face perception and object identification, in the sense that you would need to know what that problem is all about, and then you would learn about how convolutional neural networks would solve this problem. And same thing for algorithms. So again, knowledge graphs can help here. Of course, I'm leaving out a lot of the details and just giving you the main idea of how that works. So these predicates that we have, or the relationships that we have, directly indicate aspects, right? So if you have application of as a predicate, then the terms that are there, feature selection and so on, this application of itself is an aspect, and feature selection is related to that, right? Similarly for algorithm for, so backpropagation is an algorithm for neural networks, and CNN is a type of neural network. So through this transitive relationship, you can say that if the aspect that you're interested in is algorithm for, then backpropagation might have something to do with it. So again, as I said, I'm leaving out the details of exactly how we go from having these triples here in the knowledge base to generating these prerequisites. But this is the idea that we pursued, and we came up with a method of separating out the prerequisites based on the aspects. And I urge you to go read our papers for more details. And this is just to give you an idea of the kind of precision that we get. Preface is our method, which is at 0.76, which is reasonable, but it really does have quite a lot of scope for improvement as well. So then I want to talk about an application using the biochemical knowledge base that is down here. And this is an example of an application where we did not really succeed. So this is like a half-done sort of work, but I thought it would still be interesting because some of you might be interested in taking it up and sort of completing it, right? So the task here that we were given is to determine if a microbe is aerobic or anaerobic. And the reason this task is interesting is because the presence of microbes in certain kinds of environments and the nature of those microbes could indicate presence of oil deposits. So this was from an oil company that we got this project. And the input was a large amount of literature. So this literature contains lots of different kinds of data collection and experiments that have been performed and reports of those experiments. And what they wanted us to do is to build a sort of a method to go through this literature and try to give a list of microbes which satisfy one of the two different constraints. So it should be either aerobic or anaerobic, and I should give a list of these microbes that satisfy. So we started with looking at constructing a knowledge base of that. And we were given this corpus of articles, and this was the goal. One of the challenges, of course, was that we cannot extract this relation directly because no one directly says that this is aerobic or non-aerobic. Rather, we need to infer it in some way. And that's why we went for this knowledge graph construction. So what we thought is that we could try to extract triples from the corpus, and then there would be a separate component on top of this knowledge base to reason out whether a particular microbe was aerobic or not. And for this reasoning part, we need to make use of expert knowledge, right? So it's the biochemical engineers who actually know how to infer whether a particular microbe is aerobic or not. And they could give us a bunch of rules to tell us how to infer from this kind of knowledge graph whether a microbe is aerobic or not. So there were many interesting entity types like microbes, substrates, enzymes. So these are all entity types that we were given. We were told that these are interesting, and we were told that these relations are interesting. And we did get, about 3,000 triples. And we had this knowledge base with us, but we couldn't go any further because of lack of any expert help after this point. So if you have, collaborators in the biochemical domain, maybe this is something that is interesting for you, right? So given a knowledge graph of this kind, can you come up with rules, or you're given with rules, right? You need to formulate these rules and then do inference on top of this knowledge graph to give you this particular piece of information. Okay, So those were a bunch of examples which were very domain specific and required domain specific knowledge graphs to be constructed. So now let me talk a little bit about the construction part of it. So we came up with this table, which I'm sort of grandly naming as general principles for domain specific KB construction. But these are sort of the lessons that we had learned when we, constructed all these different kinds of KGs. So one of the most important principles is this part here, which is source identification, because most of the problems become very easy if you make sure that your source is wonderfully structured and wonderfully nice. Okay, so that is one of the things, that's one of the first things that you do when you're doing domain specific KB construction. Where is the information coming from? And the cleaner the information, the better off you are. So we divided sources into two parts, structured sources and unstructured sources. Unstructured sources, it's exactly what you might think. It could be newspaper articles or blogs or forums, free-flowing text, where there is no structure apart from, there are words and sentences, paragraphs, and so on. And structured sources, the most frequently used one is Wikipedia. In fact, we have used Wikipedia in all the KG construction tasks so far. But domain-specific sources also help quite tremendously. And some of the knowledge graphs that we build, like for example, in the biochemical domain, they do have very organized databases already there on the web, right? So it's a matter of going to those websites and trying to extract the information that you want by building wrappers around them. So structured sources are a very easy in the sense it's an engineering job to write these wrappers and extract the information. Unstructured sources, they're a lot less certain. So that is the first part. Next is to look at entities. And usually, if you have a dictionary of entities, that's the best, right? So, and that's what this set of things are aimed at, right? So if you have a good dictionary of entities, then this next part, which is relation extraction, becomes easier because you always know between which entities you want to extract these relations. So entities, again, building up this dictionary of entities, you can look at it from multiple viewpoints. Again, this extraction from structured sources, which is designing appropriate heuristics and writing the wrappers. So a lot of engineering goes into play. And extraction from unstructured sources. So here, of course, lots of machine learning techniques could come into play, but we have mainly used pause tagging and heuristics to do this, right? So unstructured sources, mainly plain text. And depending on whether the type of entity you're extracting is known or unknown, you can be very specific about the technique that you use. And of course, there's always going to be a cleanup step because the entities that you extract, there could be lots of duplicates, and the duplicates are not always obvious because they're expressed in with different surface forms. So there's a cleanup step that is involved here. But at the end of it, you have a whole bunch of entities which are nicely structured, and these could be canonical names of entities, as well as the different ways in which these entities could occur in text. So then once we have the dictionary of entities, we move on to extracting relations. Again, you can divide it into both the structured and unstructured sources, relation extraction from both structured and unstructured sources. And you can further divide it into relations that you know that you have to extract and relations that you don't know about yet, but you just want to extract anyway because they might be useful sometime later. And I will be more specific about this sequence of steps. I will show you how to use them in a couple of slides. And then there is a cleanup, of course, same as with entities, there could be duplicate relations and the same relation expressed in multiple different ways. So there is a cleanup step involved here. And then there is a refinement step. So whatever you have extracted so far, entities and relationships, you can infer new entities and infer new relations. And these need not be machine learning techniques. It could be something as simple as string matching. I'll show you an example shortly about this. And of course, there are lots of different kinds of embedding methods these days, all of which aim to do this entity, relation discovery kind of tasks that are there. And you can enhance the KB through feedback, right? So whatever you have extracted now, you feedback further saying, this is the knowledge I have now. So now using this knowledge, can you infer new knowledge, right? So this refinement step, there could be a lot more, but these are the main things that we have used so far. So these are the four steps. So how do we use these 4 steps in the actual KGs that I talked about, right? So for opinion base, we used the source newspaper articles, Wikipedia and Debatepedia. So unfortunately, I just checked and this website Debatepedia no longer exists, but it's a Debatepedia was a website very similar to Wikipedia, but for debates, for politically hot topics. It had pro and con debates that would be listed there, right? For Technobase, we used Wikipedia again, but also domain-specific Webopedia and TechTarget, which are IT-related websites, and textbooks, digitized textbooks that we could find online. Biochemical KB, again, research articles were the main source. But we also had this very organized sources like Brenda and Microbes Online and so on, which were, helped a lot in constructing this dictionary of entities. So that is this column here. So event base, I didn't really talk about, so I'm just going to leave it. It is again another project which is like sort of half done. It did not really go through to completion. We did not get the kind of applications that we wanted, but it was a good experience for us to, again, build a very specific kind of knowledge base based on just events that occurred, during the lifetime of a particular presidency or a particular set of years and so on. So entity extraction techniques, I will go through this in a little more detail in the next slide. So opinion base, of course, is 10 years ago, and we could use names of entities from Yago, which was the main knowledge graph. It is still prominent to this day. Yago, of course, derived from Wikipedia, and we could made use of Debatepedia. Again, the article titles in Debatepedia are directly entities or topics there. And we know the types that we want. We want people and political organizations. So we could directly extract these entities from these places, right? And Technobase, again, the same thing. Wikipedia and Webopedia, TechTarget, article names give us these entities. But though we don't know the types of these entities, this is a relationship that we have to extract further. And we found one very interesting thing, looking at the indexes of online textbooks. It's a very rich source of entities, right? So anytime you read a textbook and you want to search for a particular topic, you go to the index, and these topics are nothing but entities which are interesting for us. Biochemical KGs, we made use of a lot of expert curated lists. So as I said, in this domain, there are lots of very nice databases, large and comprehensive databases out there. So all we need to do is get the information that we need from these databases. And we also used web sources. So that is, okay, so web sources were these online databases. Expert curated list is what we got from the company. And we also looked at pause tagging and heuristic from research articles. So that was the last part of it. So relation extraction for opinion based, there is only 2 relations, support and oppose. So they are known relations, but the source from which we need to extract is unstructured sources. For techno-base, there were some relations that we knew, some relations that we did not know. And we extracted known relations from structured as well as unstructured sources. Unknown relations in the sense we did not have a pre-made list of these relations. We just extracted whatever we could, both from structured as well as unstructured sources. And for the biochemical KB, we knew the relations because the experts told us that these are the relations we need to extract. And we had to finally come down to training some machine learning models because it was not so easy to extract these relations from any of these simpler methods or easier methods that were there. Right. So instead of talking about the refinement part, let me show you an example of how we made use of these 4 different things. So this is the opinion base that I was talking about. So the first part was dictionary creation. So dictionary of entities. So the entities that we are interested in are stakeholders, which are people or organizations, and topics like the Afghan peace process. So as I mentioned before, Wikipedia and Debatepedia both have, these article titles. They directly give us the entities. So we just need to ensure that these entities make sense. So there is some amount of post-processing, but for the most part, we could get these stakeholders from Wikipedia and these topics from Debatepedia. And then there were only 2 relations. So the relations are known. Support and oppose are the only 2 relations, but the source is unstructured, right? So the simplest thing that we can do is to, ask for exact string match, right? So he supports is a string that we want to match, and we just give it on Google, he supports, and then we get a whole bunch of candidates from which potentially we can extract these relations. So Afghan president says he supports talks with Taliban. So what we need to extract from this sentence here in the headline is the subject, which is the stakeholder, Afghan president, and the topic, which is talks with Taliban. And that we can do using NLP techniques, which are sometimes reliable, many times not so reliable. So once the relation is extracted, we need to canonicalize them. So at the point, in 2012, Afghan president was Hamid Karzai. So Hamid Karzai, if we can get from Wikipedia, we also get certain alternative names for Hamid Karzai. So this screenshot is from yesterday. So it only looks at, if you type in Karzai, which is an alternate name, it leads to this page. But at the, in 2012, president of Afghanistan president, that would lead to this page as well. So apart from having Hamid Karzai as an entity, we also know these other ways in which Hamid Karzai would be referred to. And we can make use of that to canonicalize. So Afghan president is the subject or the stakeholder, and Afghan president is canonicalized to Hamid Karzai. Similarly, we use some different techniques, talks with Taliban, Taliban talks. These are all different ways of referring to the Afghan peace process. So this canonicalization, the cleanup part of it, right? So the cleanup part, we had to use some other kinds of techniques, which I'm not talking about, but you can look it up in our papers. And then one interesting thing about this knowledge graph is there is no taxonomy. So there is no type of relation. Rather, there is a subtopic relationship between, especially between these topics of interest, these politically hot topics like drone strikes, Afghanistan peace process. These are subtopics under a broader umbrella like Afghanistan war. Similarly, Afghanistan war, Iraq war, they were all part of the war on terror, right? So these are subtopic. Instead of having type of relationships, we have subtopic of relationships. And of course, I'm not talking about the methods by which we constructed this hierarchy. You can look at the papers for more details. So this is regarding the opinion base, and I will briefly talk about. So before I move on, we had about 29,000 extractions of this kind, and the precision was about 72%. So not very bad, but of course there is scope for lots of improvement in this as well. So now let me talk about Technobase, which is another knowledge graph which is domain specific. Again, we start from identifying the sources and then building a dictionary of entities. So again, looking at Wikipedia article titles, right, from the specific category of computing, we were able to extract about 54,000 entities. Similarly, from Webopedia and TechTarget, about 24,000 entities and about 16,000 entities from the indexes of online textbooks. And there were some overlaps which we were able to resolve. using some simple string matching techniques, and totally ended up with about 70,000 entities. So we have our dictionary of entities, and now we want to look at the extraction of relations from these entities. So we divided the relations that we have into 4 parts. So let me first talk about the structured sources, which is mainly Wikipedia, and known relations. So known relations, how do we know these relations? It's because we made a list of relations which we thought are interesting for this domain and can be easily extracted. So that's how we know that these relations are what we want to extract. So here are some examples of the different kinds of relations we can directly extract from Wikipedia, right? So if you consider the first one, which is the type of relation, then you go to this page called list of data structures, right? And we know that trees and binary trees, binary search trees, these are already there in our dictionary, entity dictionary. So these are of interest to us. And if we go to this list of data structures and look at the structure of this page, so we have trees as a subheading here. So tree is a type of data structure. So that is what we can infer here. And then we have binary trees as one of the topics. So binary trees is a type of tree. So that's what we can infer. And binary trees again is organized into a list of different kinds of trees. And binary search tree, for example, is a type of binary tree. So we can infer these relations, the type of relation, just looking at the structure of the page itself. Similarly, subtopic of. So how do we know that this page is useful to extract this? Simply looking at the fact that there is a topic keyword there. So list of set theory topics. So if that is the kind of page, there is a topic keyword here, then it is very likely that the subtopic of relationship can be extracted. Again, looking at the structure of the page, we just have to build a wrapper to extract these relations like Boolean valued model, subtopic of set theory, and so on. Similarly, for application of algorithm for, these are all looking at simple keywords and extracting these triples from them, right? So there is a keyword algorithms here under this derivative free optimization, right? So this is already a entity in our dictionary. So we know that it's interesting for us. And then you look at the structure of the page, and there is algorithms as a heading, and there is a list. So you can infer triples such as cuckoo search is an algorithm for derivative free optimization, and so on. So this is structured sources and known relations. So we could also do relationship extraction in different ways. When it is still a structured source, but we don't know what relation we might be getting. And this we mainly did by looking at this structure called templates. So if you look at Wikipedia, you see these tabular structures somewhere near the bottom, right? So they look at different kinds of interesting entities related to databases like this. So considering the row headings, row headings as the relationship, and databases is of course in the object here. We can infer the relationship that view is an object in databases. Data dictionary is a component in databases, and so on. So this was not a very accurate way of extracting relations, but we did do so because we did get interesting relations out of it. So, and again, these are unknown relations, right? So for each entity, there could be different kinds of row headers here. And then we looked at unstructured sources. So that was about structured sources where we knew the relation before and then we did not know the relation. Now this is an unstructured source, but we know what relation we have to extract. And the main relation we extracted here is this synonym of relation, which we could extract simply by looking at string matching, right? So if you match something like is abbreviation for, so there will be like X is an abbreviation for Y. And you have an entity of interest to you. So BFS already in our entity dictionary, we know that it's of interest. And then in brackets, there would be an expansion of that saying that it is breadth first search. right? So an entity of interest and something in the brackets, you can extract the synonym of relation between the two. And same thing with is short for. So those were some synonym of relations that we extracted. And then, of course, at the time, we had to look at unstructured source and unknown relations, which is basically looking at OpenIE, which is a running project at this time, many years. But one of the big problems with OpenIE is that it throws up a lot of junk, right? So we ran OpenIE on Wikipedia articles, right? So it generated something like 400,000 triples. And we had to do a number of different filtering steps, including making use of our dictionary to make sure that the entities make sense, right? So that is like the second step that we did. We just removed entities that were not in the dictionary, right? So reduced it by 100,000, but that's really not enough because the kinds of things we were getting, so many of them were just junk. So after a lot of effort with these different kind of filtering steps, we narrowed it down to about 3,520 triples. But when we evaluated the accuracy, it's only just 65%, right? So I wouldn't recommend this method unless you're like really sure what these filtering steps should be. But we did get some very interesting relationships, right? So gigabit Ethernet is a high-speed form of Ethernet. These kinds of relations, which you could not have listed before, these relations were thrown up by OpenIE, which are very interesting, but they're also very sparse. Right. So I will just skip the refinement part of it. So this was just using the neural tensor networks. That this is the method that we used to do a sort of link prediction on top of the technobase that we already had, and it gave us some interesting results. Let me not talk a lot more about it because I think I'm running out of time. So I think, yeah, so just some statistics before I conclude. So technobase, of course, is available from GitHub, and we had totally about 70,000 entities, 2,500 relations. And we also looked at, so totally about a little less than 150,000 triples. And we also looked at overlap with DBpedia and Freebase. There is not a lot of overlap. And the accuracy numbers are as follows. So this is looking at the top 5 most frequent relations in technobase. And in some cases, like synonym of, it was like 100% accuracy. Any sort of extraction from unstructured sources, not very good accuracy. And the inferencing part, which I didn't really talk about 64% accuracy. So this is what we had. Right. So to conclude, I talked about applications using opinion base, which is a knowledge base for opinions, technobase, which is a knowledge base for computer science, and biochemical KB, which didn't really have a name. So it's because it sort of incomplete. The reasoning part did not work out for us. And our experience based on constructing these knowledge bases, we sort of have a recipe for how to go about constructing domain-specific KBs. And I would say the most important part of that is to identify good sources and to construct a dictionary of the interesting entities. So the entities which are of interest to the particular domain. So I will conclude with that, and thanks to all my collaborators and co-authors over the years.
Okay, thank you very much, Professor Maya. This was, I think, very interesting, at least for me, where we went through the whole breadth of it in terms of how the work evolved, progressed. And for me, I think, the general principles that you shared was very, very interesting. I would also like to thank you to talk about on the biochemical KB part, because I think it's we usually talk about successes, but I think it's very good that I think as a research community, if we talk about problems that were hard or why some things failed, then I think helps, I think, the other researchers to know that, oh, this direction didn't, and if they want to try out some other direction. So once again, thank you very much for that. Unfortunately, we are, dot at the end of our time. So apologies that we won't have too much time for Q&A. If there are questions, can you please put it on the Slack channel, and we'll coordinate with Professor Maya and try to get the answers back to everyone. Okay, with that, thank you once again, everyone, for joining in, and thank you, Professor Maya, for a great talk. This talk will be streamlined on our YouTube channel as well. So in case you missed it, or if you think you want to pass it to your colleagues, please feel free to do so. And also, I think, visit our Data Conversations website to know about other upcoming talks. Okay, with that, thank you once again, everyone. And with this, we end the session. Thanks.
Thanks. Bye.
Bye.
Thank you, everyone.